Okay, chapter 18, it's a pretty quick chapter. It won't take you too long to get through this one. It's pretty easy stuff. It's very similar to the law of averages. So we talked about the law of averages when we looked at like coin tossing and said as you toss a coin more and more, the percent of heads is going to get closer and closer to 50%. Central limit theorem is similar to that, but it's referring to the normal curve. So, sorry, this histogram or this page got warped as it transferred into this program here. The histograms we saw in chapter 3 are called empirical histograms because they represent actual data. So empirical equals real data. And that's the histograms that we looked at there. Oops, sorry, my phone is on sound apparently. We are going to look at probability histograms now. So the probability histogram represents the chance. So let's say I'm rolling 2 dice. And we have various options for the dice. You can get a 1 and a 1, or a 2 and a 1, or a 1 and a 2. There's 36 total different options. And we talked about this in chapter 13 and 14. We even had a slide where it showed all the 36 different combinations. This probability histogram right here shows the total number of spots on the 2, the probability of each of those happening. So to get a 2, or actually let's do a 7. To get a 7 when you roll the die, we have a few options. You can get a 1 and a 6, or a 6 and a 1. Oh, that's an 8. Okay. Or a 2 and a 5, or a 5 and a 2, or a 3 and a 4. Or a 4 and 3. So we have 1, 2, 3, 4, 5, 6 different ways to get a 7. So there's 6 out of a total of 36 different options. With those options, or with that, you can change that to a percent. That's approximately 17% if we round to the whole number. So looking here, we can see, oh, that is at 17%. Versus a 2, there's only one way to get a 2, and that's just snake eyes, a 1 and a 1. So there's a 1 out of 36 chance of that happening. So we can see the really small percent of that happening right there. So the probability histogram just shows the chance of each of these events happening when you roll 2 die. So yeah, probability shows the chance, and you do that by calculating that chance and then making a histogram for it. The empirical histogram we talked about on the first slide shows what actually happened. So if I repeat an experiment over and over and over again, then I can make an empirical histogram to show how many times I actually did get each of the different sums of the die. And here is the important thing. This is called the central limit theorem. It says the more repetitions we do, the closer the empirical histogram will get to the probability histogram. So again, that's saying as we do the experiment over and over and over again, what we get is going to get closer and closer to what we would expect to get. So this is what we get. This is what we expect. Another word for get is observe. Okay, so here's an example where somebody did roll 2 dice 100 times, and we can see the different results here. All of these are the number or the sum of the 2 die. If we make a histogram showing how many times we get a 2, how many times we get a 3, all the way up to a 12, the histogram looks like this. So then they went on and did it 1,000 times and got this histogram. Ooh, look, that's basically the normal curve or the probability histogram that we see down here. Same thing with this one, basically the probability histogram. So each of these are the empirical ones. This one circled are empirical because that's what actually happened, versus the probability histogram is what we would expect to happen. And the main thing here, that central limit theorem, is what we expect to happen is basically the same thing as what we get happening when you do the experiment enough times. It works even for products. So this is what we would expect to happen for multiplying the two numbers. Notice there's some gaps here because you can't get 13 from two different numbers on a die by multiplying them together because 13 is prime. Same thing with these gaps and these gaps. I don't really care about the products because we're not going to focus on products in this class. But just so you know, it does work on products as well. The histogram, empirical histogram, will look similar to the probability histogram or exactly like the probability histogram with enough repetitions. Again, I don't care about the products because we're not going to study the results of products. Okay, the probability histogram will follow the normal curve if the number of draws is large enough. Even if the tickets in the box do not follow the normal curve. So what that's saying is if I roll a die, I have 6 different options. I'm just going to write the numbers here instead of drawing the die. Dots. Okay, so if I draw a histogram for this, we get 1, 2, 3, 4, 5, 6. There's equal percent chance of getting a 1, a 2, a 3, a 4, 5, and a 6. So that's for one single draw, the chance of getting those draws. Or those tickets. Which means this histogram I just drew to represent the chance for one single draw from the box, it doesn't show it is not the normal curve, but we're looking at the sum of 2 draws. This will follow the normal curve. So it's okay if the box doesn't follow the normal curve because when you sum the results, the histogram does follow the normal curve. Main thing to know on this is if your sample is large enough and it's random, it will follow the normal curve. Okay, so we see these formulas again, EV sum and SE sum. I'm not going to spend much time on this. Just know that you still need to know those formulas. EV sum is the number of draws times the average. SE sum is the square root of the number of draws times the SD. Okay, don't care about that slide. I do care about this slide. So here's our box. So let's say we're flipping a coin. This shows the number of heads for 100 tosses, 400 tosses, and 900 tosses. And you can see it is following the normal curve with enough tosses. Same thing with this one with enough tosses, 400 tosses, even though this histogram does not follow the normal curve. With enough tosses, the sum of the draws does follow the normal curve. Same thing here. And even here, so this is a weird histogram because we're missing 3 through 8 for tickets in the box. So the histogram starts out really weird because we've got all these gaps where we don't have 3 through 8. But with enough draws, it does follow the normal curve. Okay, these will follow the normal curve, or the sum will follow the normal curve, the averages will follow the normal curve, and the percentages will follow the normal curves. So if you're asked to find a sum, an average, or a percent, it's going to be normal and you're good to go on it. If you're asked to find a product, you're not going to do it this way. And so, like I mentioned a few slides ago, we're just not going to worry about products. We've already talked about sums, EV and SE sum. We're going to talk about EV and SE averages, and then EV and SE percentages in the next couple chapters, in chapter 20, 21, and 23. We already talked about that slide. Okay, here is your homework. I think I cut off 6 and 9 for this one. Yep. And this is due Friday, April 24th. Let me know if you have questions. Thanks, you guys.